All right, so today we're really happy to have Adam Harper from the University of Warwick speaking on low moments of character sums.
Great, so thank you very much, and thank you for the invitation to speak here. Very pleased to be able to do it. So the talk is about sums of characters, which means Dirichlet characters. So the plan is that first there'll be a bit of background, reminder maybe, about Dirichlet characters and their sums and the kind of things we'd like to know about them. And then I'll state a result about the moments, which means the power averages, these sums of Dirichlet characters. And then I'll talk about the proof, and the way that the proof will work is that there'll be a random model problem, which needs to be analyzed. And then we'll try and transport some of what happens in the random model problem over to the deterministic problem with the character sums. And if you've heard me give a talk in the last couple of years, it's quite likely you'll have heard me discuss this random model problem. So the plan for today is not to say so much about that. So I'll just say enough to kind of give an idea of what's going on there, but to talk more about the kind of number theoretic part. So how you transfer what goes on in the random case over to the character sum. I'll say a little bit about both points. So throughout the talk, I'm going to be working modulo a prime. So R is going to be a large prime because P and Q will be used for other things. And chi is going to be a Dirichlet character mod R. What does that mean? So it's a character of the multiplicative group mod R, but thought of as a function on all the natural numbers. So even more explicitly than that, what are these chi? What are these Dirichlet characters mod R? So they're functions that map the natural numbers into the complex numbers. They take the value 0 if and only if R divides n, because R is prime here. And then the important conditions are these two. So chi is periodic mod R. So it means that chi of n plus R is the same as chi of n for all n. And also chi is totally multiplicative. So chi of n times m splits up as chi of n times chi of m for all n. So you have an additive condition here. The periodicity is like an additive property, and also multiplicative condition. This is what makes Dirichlet characters interesting. So usually when things are interesting in number theory, it's because there's some kind of combination of additive structure and multiplicative structure, and that's what you have. And Dirichlet characters are quite interesting. They come up a lot. They especially come up when you want to understand the distribution of interesting things like primes, in arithmetic progressions, more. So they've been quite well studied for, well, at least the last 100 years, I guess the last 200 years since Dirichlet introduced them. And the combination of these properties makes Dirichlet characters quite rigid. It means, in particular, there are only finitely many different functions that have these properties. So there are Euler-Tauschig function of R, since R is prime, that's just R minus 1 of these Dirichlet characters mod R. And some examples of such functions are, well, the function that just takes the value 1 if n is co-prime to R and 0 otherwise. So this boldface 1 is my notation for the indicator function. So you can check that this satisfies these properties. And this one is called the principal character. It takes the value 1 almost all the time. And sometimes we want to exclude this one from the analysis because it behaves a bit differently than the others. So it says here, chi a non-principal Dirichlet character. So it might not be this one. Another example would be the Legendre symbol, m mod R. So remember that this is the gadget that takes the value 1 if n is square mod R and not divisible by R. It takes the value minus 1 if n is not a square mod R, and 0 if R divides n. And this also is a Dirichlet character mod R. And the main question motivating this talk, and a lot of work for the last 100 years, let's say, is what happens if you sum up the values of a Dirichlet character? So how big is the sum of chi of n for all n upwards? So let me tell you a bit about that. So since chi is periodic mod R, we just need to look at sums of length x for x between 1 and R, because after that it starts to repeat. And the trivial bound for one of these sums, well, I didn't actually say in how I wrote things out here, but it follows from these properties that when chi is non-zero, it actually takes values of absolute value 1. So a priori, chi is taking values anywhere in the complex plane, but actually it has to take values on the complex unit circle. So that means that the trivial bound for this sum is just the number of terms. So this is at most x always. And this band will be roughly sharp if chi is the principal character. And it could also be sharp for non-principal characters if x is quite small compared with r. But generally, if chi is non-principal and x isn't too small, we expect this to be very far from the truth. We expect that these values chi will be sort of distributed over the unit circle, and you'll get some cancellation in the sum. So this should be a lot smaller than x. And here's a very plotted history of some of what's known about this. So Polya and Vinogradov in maybe about 1918, they proved that if chi is a non-principal character, you can have a band for this, which is like some constant times root r log r. Much stronger than this if x is r over 2, let's say, and stronger than this provided x is bigger than root r log r, but not non-trivial, worse than trivial if x is less than root r log r. And then Burgess improved this. So I think the first paper was in 1957, and then there was some more in the 60s. So he showed that if chi is a non-principal character, you get cancellation here. So this is the law of x, provided x is bigger than about r to the 1/4. I don't want to get into exactly what the little o's mean here. So you get cancellation for sums of length at least down to r to the 1/4. And assuming the generalized Riemann hypothesis, much more is true. So Granville and Sandarajan about 20 years ago show that these sums are still the law of x, provided log x over log r tends to infinity. So that means provided x is bigger than any fixed power of log r. And this condition would be best possible, actually. So we expect there to be some cancellation in these sums, even if x is very small for all non-principal characters. Okay, but how much cancellation should there be? So these are little o of x, but how big are they really? So a way to start thinking about that would be maybe to look at the average behavior. So you take the sum and you average over chi. And here's a very simple average, which I can show you completely on this slide. So let's just look at the second moment, the L2 norm squared. So we take the sum of chi, we take the mod squared, and we average over the r-1 different Dirichlet character. And what do you do? So you just open the square. So since I have absolute values here, this becomes the sum of chi of n times the sum of chi of m conjugate, because I have the absolute values. And then again, I didn't actually show you this when I reminded you what Dirichlet characters are, but it's not too hard to show. But when you average over all the Dirichlet characters mod r, what it does is it picks out if n and m are the same in the underlying group mod r. So it picks out if n is congruent to m mod r or not. So when you move this average through the double sum here, the only terms that survive are the ones where n is congruent to m mod r. And then the thing is that, so n and m are both at most x here, and I said that x was going to be at most r. So if n and m are congruent mod r, they actually have to be the same. So the only terms that survive here are the diagonal ones. So the size of this is just the number of terms in the original sum, so 4 of x. And this equality, actually, for the second moment, this is consistent with all of these sums, or many of these sums, being about square root x in size. Because if these were all about square root x, then the square of them would be about x. And when you took the average, you get about x, so about what you do get. And this is what we might call square root cancellation, because the trivial band here is about x, and this is square root of the trivial band. And so the question I want to ask in this talk is that really the size that these sums usually are? So since the second moment is about x in size, by Markov's inequality or Chebyshev's inequality or something, you can deduce that there can't be too high a proportion of these characters where this is much bigger than root x. Okay, the proportion of characters where this is bigger than 10 root x is going to be at most 1 over 100, something like that. But it could be that actually a lot of the time these sums are rather smaller than square root x. And the reason that this second moment has size about x is because there are just a few which are bigger. We're inflating the size. You can't tell that just from looking at the second moment. And so that's the question I want to ask. And that's what the theorem I'm going to tell you in just a minute is about. But before I get onto that, I want to just mention one older piece of work again. So this is a result from about 40 years ago of Montgomery and Vaughan. So they showed that, so again, X is anything up R, and Q is any positive real exponent that you want. And they showed that if you average over the non-principal characters, so now it is important to remove the principal character if Q is big. So if you average the 2Q power, this is bounded by some constant, which depends on Q times R to the Q. And if you know this result, the result is stronger, as you can take a maximum over X here, but I'm not worrying about that in the statement. Okay, so what can we say about this? Well, this improves on the Polyvillin-Radolph bound on average, because the Polyvillin-Radolph inequality said that these non-principal character sums were always at most root R log R. And if you plug that in here, you get root R log R to the power 2Q. And the bound we actually have is R to the Q, which is square root R to the Q. So on average, you can get rid of this log. Another thing you can do with this result, so if we take X to be R over 2, let's say, or any fixed constant less than 1 times R would also be okay. And you take Q to be, let's say, 2 here, so you look at the fourth moment, then this will tell you that the fourth moment is at most R squared, so of the order of X squared, if X is something like this. And then we know from here that the second moment is equal to or lower bounded by about X. And so if you compare those pieces of information using Holder's inequality or something like that, you can deduce that in this case, so if X is R over 2, there will be a positive proportion, a fixed positive proportion of characters mod R, where this sum has size of the order of root R, which is the same thing as of the order of root. So in this case, when X is R over 2, the answer to the question I asked here is the typical size of these about root X is, well, yes. At least there are a reasonable proportion of them that will have size about root if X is R over 2 or some other fixed constant times. Okay, so that's great. But as with the original Polyvillin-Radolph bound, this doesn't improve as X gets smaller. So it's uniforming X, so good. But you'd expect that when X is smaller, so you're summing less stuff, the size should generally be less. You don't see that in this bound. And that's what the theorem I'm going to tell you about on the next slide is about. So what can you say about these moments if you want the bound to depend on X? Okay, so here's a theorem. So as always, R is a big prime and X is between 1 and R. And I'm looking here at the low moments. So trivially, we were able to handle the second moment just by expanding things out. So I'm looking here at the 2Qth moment where Q is between 0 and 1. And maybe if I just go back to the second moment. So the second moment was like X in size, roughly. So by Holder, you could deduce that the 2Qth moment, the Q between 0 and 1, is at most about X to the Q. Because Holder lets you go up the higher moments. So the trivial kind of band would be like X to the Q. And the band in the theorem is X to the Q divided by this complicated looking denominator. Okay, so let's look at this. So if Q is equal to 1, then this denominator just goes away, which we knew it had to do because we knew the exact size of this when Q was 1, and that was like X to the Q, X. Also, if L is bounded in size, so L here is being defined to be the minimum of X and R over X. So if X is bounded or R over X is bounded, then this will just be a fixed thing again in the denominator here, and this denominator you won't really see it. So again, you'll just get the trivial bound X to the Q. And this is basically what's going on in the Montgomery-Vaughan situation. So I said that when X is R over 2, you get a band like R to the Q, and that turns out to be sharp because you have this positive proportion of characters where this is of the order of root R. So this is exactly the kind of situation where L is bounded because X is kind of close to R. If X is R over 2, then R over X is just 2. So you don't see this denominator here. But if X is growing and R over X is also growing, so X is tending to infinity, but X is little o of R, then this denominator will do something. So in particular, maybe just to make it look nicer at least, you take Q to be 1/2, so you get the first absolute moment on the left-hand side. Then what's the bound? So you get x to the 1/2 in the numerator. This is just a constant now, this 1 minus Q, if Q is 1/2. And then we're taking square root log 10L to the power 1/2. So log 10L to the power 1/4. So as I said, if x tends to infinity, but x is little of r, and L is tending to infinity, so this denominator here is growing. So this is little O of root x in this range. So in this case, the first absolute moment is little O of root x. So you have more than square root cancellation in the first one, slightly more than square root cancellation. And that tells you that the answer to the question that I asked here is the typical size of these, usually like root x, is none. Because if you apply Markov's inequality to this first moment bound rather than applying it to the second moment bound, it will tell you that for most characters, this is bounded by some constant times root x over log L to 1. So I think this is quite interesting because you don't usually see more than square root cancellation in kind of natural number theoretic problems, certainly not ones involving Dirichlet characters. Now, the other thing you might think when you look at something like this is, so this is a fairly pathetic kind of saving that you have in the denominator here. So you might think that maybe there's really a lot more saving going on here and we just don't see it. This is all that we've been able to show. But what I'm claiming,
I'm sure you're going to get there from the beginning of your lecture. You indicated that, but if we were to think of the chi of n as random, when n is small, it's multiplicative, so you have to put in random multiplicative. There's also the reciprocity, so where you can write the sum as a dual sum.
Yes.
And so I've always thought that until where those balance, you're going to look like a random multiplicative function. Is that where you're going?
Yes. So the reason that you get the L here is exactly because of the reciprocity. So I'll talk about this in a minute. And you do get an analog of this theorem in the random case. And in fact, we'll use the theorem in the random case to prove this theorem in the deterministic case.
So then the philosophy is exactly that.
Yes.
There's the x and the r over x. That's the, in other words, if you're in the finite field, you think there's a polynomial of some degree, but it's a reciprocal polynomial.
Yes.
And so you, at the beginning, you look random, and then when you get through the square root of the conductor, you stop being random, right?
Yeah, that's exactly right.
Okay, so that's at least consistent with what I was expecting. Good.
Good. Yeah. Any other questions at this point?
Do we have a question? And if you do it with modular forms, have you done this with modular forms?
I haven't, no. So what you can do is you can put a fixed unimodular multiplicative function in here, multiplying chi of n, and you get the same bound.
Yeah, so no, but I want it to be a GL2.
Yeah, I understand.
Not modulus one, yeah.
Yes, so I haven't done that.
Okay, because I think, have you ever seen the paper of Booker disproving Katz's conjecture? Since Katz is here, we have to tease him.
No, I haven't seen it.
So Katz, he didn't conjecture, he just asked whether a certain thing of Fourier coefficients of a modular form, and so he summed this, and if it were a modular form, it would have had to turn around at square root of the conductor. So it looked random at the beginning, and then it didn't turn around, thus confirming that whatever object we were talking about was not modular.
Okay.
So it was kind of based on this philosophy of exactly that it's random initially, and then, but you've never worked out the theory for Hecker multiplicative functions?
No. So in a minute, I'll show the result for random multiplicative functions which are unimodular. So there is some work on this, not by me, but by other people, trying to extend this to functions that aren't bounded by 1. So this would be some kind of random analog of the higher weight case. But I don't think anything's been done for the genuinely number theoretic problem outside this setting. Yeah. Any other questions?
Is this I don't know, it makes me think a little bit of like Siegel zeros and like how like for a lot of the characters you get something that's a little smaller than expected, but that allowing for like a few bad things to happen. But you know, I may be way off. Sorry.
So I guess it's like that in the sense that it says the second moment is the size that it is. So the second moment has size like x, because there are a sort of small number of characters where this is a bit bigger than root x, and for most of the characters it's smaller. So in that sense, it's kind of vaguely related to what happens for sequel zeros. But the cause of this extra saving is not anything to do with sequel zeros, so far as I know. Sequel zeros, of course, probably don't exist, whereas this is an actual theorem.
Yeah.
So this is a saving that does exist.
In New Jersey, we say Landau sequel zeros.
Okay. Other questions? Okay, so I think I was in the middle of saying that I conjectured that this rather pathetic saving was probably sharp. So the reason for that is because in the random case that we'll come on to talk about in just a second, there is a matching lower bound here. So I can't prove a matching lower bound in the theoretic case yet, but for the random problem, you do have one. And I would conjecture for that reason that this should be sharp in the number theoretic case as well, like it is in the random problem. Okay, so what is this random model that's been discussed a little bit? So we want a model for a randomly chosen Dirichlet character model. So of course, just picking a Dirichlet character uniformly random, that is a random thing, but it's not so easy to analyze that. So we want a kind of simpler random model. We might be able to get a handle on a bit more using probabilistic techniques. And this is what it's going to be. So on the primes, we're going to define our random function be independent for every prime and just uniformly distributed on the complex unit circle. And random variables like that are called Steinhaus random variables sometimes. And then we're going to extend the definition to a function on all the natural numbers in this multiplicative sort of way. So to get f of n for general n, you just look at the prime powers in the prime factorization of n, and you multiply together the appropriate number of copies of f of p. And so these functions, they're random because the f of p's are random. They take values on the complex unit circle, like Dirichlet characters do, and they have this totally multiplicative property. So f of mn is equal to f of m times f of n for all m and n because of the way I've defined f of m. So they have one of the important defining properties of Dirichlet characters, the multiplicativity, but they don't have the other one. They don't have the periodicity. There's no R here. There's no kind of conductor. So the question is going to be, but kind of in compensation for that, we get the f of p's to be independent for different primes. So we couldn't possibly have that if we tried to impose periodicity. So the question is going to be, by dropping this periodicity property, do we have something that's still close enough to the Dirichlet character setting to be able to transfer the results across or not? And if you haven't seen this kind of thing before, I don't know what you'd think. I think you might think that we've kind of lost a lot by getting rid of the periodicity. But it turns out actually that in a lot of problems, these random functions are a very good model for randomly chosen Dirichlet characters. Basically, provided you can formulate your question in a way that you don't get too close to the periodicity. So this is kind of what Peter was saying. So if you don't have to deal with sums that are very long and you actually see the wraparound mod R, then the random model, where there is no wraparound, there is no conductor, might still tell you something about the Dirichlet character. And even if you are working with quite long sums, you might be able to do something to get around it. And this is what we'll see in a minute. So let me just show you a few calculations in this random case to kind of mirror what we did for Dirichlet characters. So for Dirichlet characters, we looked at the average of pi of n bar, and that turned out to be just the indicator of whether n is congruent to n mod r or not. And if you do that for the random multiplicative function, if you plug in the definition, when you take the conjugate of f of m, instead of having f of p to the power b here, you get f of p to the power minus b, because everything's on the unit circle. So that's what happens when you take conjugates. And then, so if n is equal to m, all the prime powers here will exactly match the prime powers here. So everything will cancel out. So you just get 1. And if n is not equal to m, then there'll be some prime power here that doesn't exactly match the corresponding prime power here. So you'll have some f of p's left over. And then the f of p's all have mean 0. So you'll just get 0. So when you do this in the random multiplicative case, you just get 1 if n is equal to m and 0 otherwise.
Can you remind me, there was a theorem of a fellow who was near Stanford. I remember him coming and showing Paul Cohen often. I think it was at Santa Cruz, that if you take a random Euler product like this, the Riemann hypothesis is true, but the natural boundary is at the half. Is that correct, or is it zero?
That's correct, yes.
What's the statement? The
Yeah,
random Euler.
So if you look at the partial sum of f of n, this is big O of x to the 1/2 plus epsilon, almost surely. And you can prove this by looking at the Euler product. You can show the Euler product almost surely converges strictly to the right of the 1/2 line, and it has singularities on the 1/2
So
line.
it's got a natural boundary. Okay.
Yeah. Right. So if you look at the mean square, you open the mean square just like we did in the character sum case. Now, when you compute the average, instead of getting the indicator that n is congruent to m mod r, you get the indicator that n is equal to m. And so you just get, again, the diagonal conclusion here. So you get the floor effects. So you get exactly the same answer for the mean square as we did in the character sum case. But in the character sum case, this worked because we were insisting that a and m were less than x, which was less than r. So we had a condition that n is congruent to m mod r, and that just reduced to a condition n is equal to m. Here, there is no r. So this would be true for any x. Okay, and since the second moment is x, then by Holder, you could show that the first moment is at most root x, just like you could in the character sum case. And here it was conjectured by Helson in 2010, and I won't get into why he conjectured this, but he did. So he conjectured that the first absolute moment should be little over. So you should have more saving. And you do. So here's the theorem, which I proved a few years ago, but it was published last year. So f is one of these random multiplicative functions. X is large, q is between 0 and 1. And the statement is that the 2qth moment, so the average of the 2qth power, is of the order of x to the q divided by this denominator. So if I go back maybe to theorem 1, so this is what we had in theorem 1, and this is what you have here. So it looks very similar. Let me just emphasize here, so this is an order of magnitude statement. So this is bounded above by some constant times this, and also below by some other absolute constant. So in the random case, you have upper and lower bounds. We don't have lower bounds in the character sum. Yeah. So in particular, if you take q to be 1/2 here, like we did for the character sums, you get that the first moment is of the order of x to the 1/2 divided by root log x to the 1/2. So root x divided by log x to the 1/4. So you get a bit more than square root cancellation. So this conjecture is true. And as we already discussed, as Peter was saying, so what's the difference between this statement and what we had in theorem 1? Well, the difference really is that here we have log x as the saving, there we have log L, basically. And the reason for that is because there's a duality, a kind of symmetry between the sum up to x and the sum up to r over x. It comes from Poisson summation or the approximate function equation, something like that. So the sum up to x is like a scaled version of the sum up to r over x. So you can't reasonably expect to get more saving than comes from whichever is the shorter of these two sums. And this is where you see the periodicity. So for the random multiplicative function, there is no period, there is no conductor. So nothing like L would make sense to appear. But in the Dirichlet character case, there is. And you see that in the appearance of this L, in the kind of flip that you can do between these two things. But apart from this, or apart from this thing to take account of the periodicity, the answer is the same in the character sum cases in the random. Okay, so now I want to talk a bit about how you prove the upper bound part, at least of this theorem, in the random case. And then we'll see how you can try and transport that over to the character sum case. So there are two steps. So first you show that the 2qth moment of the sum is some scaling factor, some x to the q, which is what we want here, times a qth moment of kind of square average of the Euler product that corresponds to f. So this is the product for the primes up to x, the same x as here, of the usual kind of Euler product terms with the random f of p's. So don't think it's obvious that something like this would be true. But if something like this is true, at least you could think that you are making some progress, because on the left, you have the f of n's. The f of b's are all sort of multiplied together. They're very dependent. On the right here, you have the order product. And in the order product, these different terms are independent. You're multiplying together things corresponding to different f of p's, and the f of p's are independent Steinhaus random variable. So the thing on the right maybe looks easier to handle than the thing on the left. The kind of complicating factor is the fact that you have the integral on the inside. So you take the expectation of the qth power, and on the inside you have the integral of the 1 square. Okay, so the first step is to show something like this, and then the second step is well, you have to analyze that and show it to the size that it's supposed to be. Okay, so the second step is much more interesting, really, from a probabilistic point of view. So there's a connection between these averages and something called critical multiplicative chaos that physicists study. So if you know what that is, then good for you. And if you don't, I'm not going to talk about it today. I'll just say one thing to give a little flavor of what goes on here. So a trivial thing you could try to do to bound this is you could use Holder again. So you could try to upper bound this qth moment by the first moment. So what would happen? So it would tell you that you could upper bound this by moving the expectation inside, basically. And then you could move the expectation through the integral as well. So the expectation would get to here, to the mod squared of the order product. And this is an order product of length x. And this is like the average of a unitary L function, basically. So this second moment will come out to be like log x. And this will cancel with the log which is there. And then this has length 1. So you'll get a band like 1. And remember, what we're shooting for here is something a bit better than 1. So we want this saving here to give us the saving, which is. So how do you get that? Well, what you should do is you should restrict to the case where the order product, but not just the order product. And this is kind of an important thing that comes from thinking about this connection. So not just the product up to x, but also various of the partial products, so over smaller ranges of primes, satisfy some size bounds at some points h, some kind of net of points h. And what you need to show is that it's okay to restrict to that case, that you don't kind of lose too much by doing that. And also that if you restrict to this case where you impose this kind of growth condition, then you can improve this bound. And that's quite interesting, but it's all probabilistic, so I'm not going to talk about it today. I just want to talk about the first step. So how do you do this? And this uses conditioning. So conditioning means freezing some of the randomness. So you have a lot of randomness here coming from the f of p for different primes p. And what we're going to do is we're going to fix some of them in parts of the proof and just use the randomness that comes from the others. And then we're going to re-randomize over all the ones that we fix. And another way of thinking about this, if you're not so used to this probabilistic setup, is if you just think of it as a kind of big multiple integral, which you would do using Fubini. You fix some of the variables, you integrate out the others, and then you have the variables left that you fix. Okay, so we'll see on the next slide how this comes into things. So to simplify things, I'm just going to talk about the upper bound, because that's all we get in the character sum case anyway. And I'm just going to talk about part of a sum that has a big prime factor, the numbers that have a prime factor bigger than square root x. So this is obviously not all the terms in the sum have this property, but this is a positive proportion of all the terms in the sum that satisfy this. And these numbers, they have one prime factor bigger than root x. They can't have two because they're not big enough to have two prime factors of this size. So these numbers look like some big prime times some other bit, some m, which is at most x over p, in order to fit into this. And since f is multiplicative, f will split up into f of p times f of the other bit. So we can rewrite this sum like this. So this is a sum over the large prime, f of p, times the other bit, sum over m up to x over p of f of m. Okay, so we'll leave that in abeyance for a minute, and I'll talk about the conditioning. So I'm going to let expectation with a superscript kind of root x, being expectation condition along all the values of the f of p for p up to root x. So expectation where you freeze all these, where you think of these as being fixed constants and you just average over everything else. So this conditional expectation, this will be a function of these things. So if I apply this to something, the answer will be a function of these f of p's. Okay, so I want to compute the 2qth moment of this sum. I can write it as the full average of the conditional average of the 2qth power, because it's like first you average with some of them fixed, and then you average over the fixed ones, you average over everything. And then I can apply Holder, but I'm only going to apply Holder to the inner expectation, the conditional expectation. So I'm going to apply Holder to get up from the 2qth moment to the second moment. Remember, q is less than 1. So if I apply Holder here, it will tell me this is at most the expectation of the qth power of the mean square with the conditional average. So now these expectations are separated, because this one's on the outside, then I have a qth power, then I have this conditional expectation in the middle. And now if we go back to this expression I had here, so if I take the expectation conditional on the values of f of p for all the small p's, then this thing on the inside is fixed, because this depends on the f of p's for the p less than root x. And these f of p's on the outside are still perfectly random. They're not affected by the conditioning. So when you do the mean square conditional on the f of p for the p's up to root x, these are some constants. And for the p's here, you just get the diagonal terms that survive. So this here comes out to be this. So for the large primes, you just get a diagonal contribution and you sum up the mod squared of the inner sums. So these things are treated as fixed for this conditional expectation, but you still have this averaging on the outside corresponding to these sums of f of m. Okay, so let me say just a few words about how you finish this step 1 of the proof, although this will be the most important bit for transferring this to the number theoretic case. So here we have a sum over primes. Primes are quite well distributed, and their density in this interval here is like 1 over log x, roughly. So you can show that this expectation with this sum is roughly the same as an expectation with the integral. So instead of summing over primes being root x and x, you integrate over e between root x and x. If you put in this factor y over log x to account for the density of the primes. And then you can just make a substitution. So if you substitute z is x over t here, then this range of integration gets flipped around and you get a z squared in the denominator. If you work it out, you get a factor x that comes out. And this is all raised to the power q, so you actually get factor x to the q that comes out. And this is the factor x to the q that we were hoping for, factor that's here. And then, so what do you have here? So this is some kind of average with these weights z squared of the mod squared of these sums of f of m. And there's a version of Parseval that you can apply to this. So you can apply Parseval's identity multiplicatively, Parseval's identity for Dirichlet series. It will tell you, quite roughly speaking now, this isn't really quite right, but something like this. So it will tell you that this integral average of the mod squared is something like integral average of the mod squared of the Euler product that corresponds. And this is what I was claiming we were going to show in this step. Okay, so if you didn't really follow what I said here, doesn't matter very much. Let me just point out, so the things on this slide don't use the randomness in a very serious way. So we're using the fact that the primes are quite well distributed. You slightly use the fact that you're doing some averaging when you perform these steps properly, but not very much. So you don't need to know that you have all these independent f of p's underlying this step. And here you don't really use the randomness at all. So this is Parseval's identity applied deterministically to the thing that's on the inside of this bracket. So the expectation, the qth power doesn't point. So you could reasonably think that this part we might be able to do in the character sum case. So that leaves this. So here we're conditioning. So we are using the randomness in a serious way. So is it going to be possible to do something like this in the character sum. So what I want to do for the last 15 minutes or so maybe is talk about that.
Okay, before you turn to that, do you have a theory which is like whoever's theorems there are about the random walk, or if you take +-1 at random, you square root x, but then there's a log, and there's a 0-1 law and a Brownian bridge. Do you have all those?
So for the random multiplicative case, you get a lower bound like root x log x to the 1/4, almost surely. And it's work in progress to get maybe a matching upper bound. So the best that's known at the moment is root x log x squared, roughly, as an almost sure upper bound. Well, I would conjecture that 1/4 is the correct component.
And is there sort of a connection with a Brownian bridge, as there is in that case?
So there's a connection with a Brownian bridge. There's a connection with a random walk, because if you get the square root log for the simple random walk, because it kind of corresponds to Gaussian fluctuations at a certain set of test points, where the square root log comes from, or the fluctuations of a Brownian motion is the same thing. So if you do enough conditioning, you can also find something that looks a bit like a simple random walk in the random multiplicative case.
I see. Inside it.
Yes. But you need to, so when you do the condition, you need to scale by something different. So this is why the exponent comes out to be 1/4 instead of 1.
Thanks.
Okay. Yeah. Any other questions at this point before I go on to the sort of number theoretic bit again? Okay, so right. So could we possibly do this for Dirichlet characters? Could we do this step 1 of the argument at least for Dirichlet characters? So we want to do some conditioning. What does it mean? So it means you freeze some of the stuff that you're averaging over, and you just average over the rest. Or if you think about it in terms of multiple integrals, you fix some of the variables and you just integrate the others. So what would it mean if you're averaging over Dirichlet characters? It would mean that you want to break up your sum over Dirichlet characters into some sort of subsums, where you fixed some of the behavior of chi in your subsums. And this is something that we could certainly conceive of doing. So you might try to do it like this. So the values of chi of b, they're some points on the unit circle. So you could give yourself some small parameter epsilon. You could break up your complex unit circle into arcs, which are small, so let's say of length 2 pi epsilon. You could try to break up your sum here according to which of these arcs all your chi of p's live in. And that would be an analog of conditioning on the behavior of f of p for all the primes up. And this actually will work, but only if x is quite small. And I want to explain why. So there's a big problem with this once x gets even sort of moderately larger than, let's say this, about log squared r. And what is this problem? So if we go back to the random model from Binet, and we ask what's the probability that our independent random variables f of p live in some arcs on the unit circle for all the primes up to root x. Well, in the random model, these f of p's are completely independent, so this is just a product of the probabilities for the individual f of p's. They live in these intervals I sub p. And what's the probability that this lives here? Well, f of p is uniform on the unit circle, so this is about epsilon. It's exactly epsilon. So this product will just be epsilon the power of the number of primes. So the number of primes here is about root x over log. So I guess I don't want the minus sign here actually. So this is epsilon to the power about 2 root x over log. And so if x is bigger than like this, about log squared r, this probability will be smaller than 1 over any power. So if I make the constant here big enough, I can make the constant c here as big as I want. And this is a big problem because if I want to say that the behavior of the character sums is sort of like the behavior of the random model, I probably want to say, if I'm doing it like this, that these probabilities are close to the corresponding probabilities, the corresponding proportions for the character sums. And that's going to be completely impossible because what's the proportion of characters for which chi of p lives in these intervals, or the proportion of characters for which chi of p does anything? Well, it might be that there aren't any, in which case the proportion is 0. Or there might be one character, so the proportion would be 1 over r minus 1, or there might be 2 characters, and so on. But the thing is that none of these things is very close to this. So they're either none, in which case you don't actually need to consider that case at all, or they're at least 1 over r minus 1 proportion, at least 1 over r minus 1 probability. So this is not.
This brings up a question that I meant to ask earlier. Is there any point, you just declared that you want to take all characters of conductor Q, why not take to average over Q a little bit further over an interval? That usually will fix this, some of this up. Do you want this pure problem? Has it got some meaning to it?
So I'll talk about an application of this at the end. You could average over the conductor as well, right, but it wouldn't help significantly with this. So even if you averaged over, let's say, all r in some dyadic interval, yeah, that would increase your number of characters from about r to about r squared, let's say, but that would still make negligible difference to the
but related to that question, is it, you're looking at families of characters and you've decided this is a natural packet?
Yes.
And just because it's the smallest natural packet, I guess, is that
sure? Yes.
Okay. Because you can't do one, of course.
Right.
Okay. Fair enough.
Yeah. So you could also average over. You could average over quadratic characters, for example. You'd expect to get that. Okay. So if you're kind of probabilistically minded, a way of saying this would be that this probability space we have here, where you just pick a Dirichlet character at random, is nowhere near as rich as this one. So this one, where you independently choose f of p, it makes sense here to talk about things of probability 1 over some big power of r. That can't happen here. So that's a problem. So I want to talk for 5 to 10 minutes about how you can fix this. Okay, so there are 2 things that we can use to kind of save ourselves here. One of these is quite standard in a lot of these problems about averages of characters and L functions and stuff like that. And one of them is a bit more specific to this problem. So the first one is that we're trying to get a saving that involves log-log. We're trying to get a saving that involves log-log L in the denominator. And log-log grows extremely slowly. And that means that instead of working with all the primes up to x or all the primes up to L, we could work with all the primes up to something quite a lot smaller than L, and log-log would stay the same size. So this would be invisible at the level of the saving that we're trying to get. So for example, instead of working with the chi of p for all the primes up to L, I could work with the chi of p for all the primes up to x of log L to the 1/3. And what's log-log of that? Well, it's log of log to the 1/3 L, so it's a third log-log L, so it's still of the order of magnitude of log-log. So this is much, much less than L, but this is still of the same size as. So we might be able to save ourselves using this, and this will help, but this won't fix the problem which is here. So this will kind of put off the place where this starts to be an issue. So instead of only being able to deal with x, which is smaller than log squared, you might be able to deal with x up to log to the power 10r, or e to the log r squared, or something like that. But you certainly won't be able to deal with x like square root r, let's say, just by doing this. So the other thing that we can do, which is more specific to this problem, is you can observe that we don't really need, the condition, we don't really need to fix all the values of all these chi. So we just need to condition on enough stuff to have control on the things that actually appear in the proof. We don't need to know every single chi of p exactly. I think it's pretty intuitive that slightly changing the value of pi of some prime about 10,000 is not going to significantly change the answer. So we don't need to fix every single one. So again, if you're thinking about this from a more probabilistic point of view, you can condition on a much coarser sigma algebra. That's what I'm saying. And that could still be enough to make the arguments go through. So let me explain quickly how you actually do this. So Instead of conditioning on the chi of p's, I'm going to switch. Now I'm going to condition on the values of these partial Euler products at a sort of net of imaginary parts. So I'm going to split up my sum of the characters according to the values of these partial Euler products at points k over log p for mod k up to log p over 2. So that means at points, imaginary points between -½ and 1/2, but spaced like 1 over log p. So I'm not going to condition on the values of the individual chi of p's anymore. I'm just going to condition on the values of these Euler products. And roughly speaking, if you know these sort of kind of well, that's enough to fix the value of this integral, x squared, by approximating the integral by a Riemann sum, something like that. And this is the integral that we expect to come up at the end of step 1 of the argument. So if we've conditioned on enough stuff to kind of roughly know the size of this integral, then we've conditioned on enough stuff. Okay, and the point is that here I only have log p things to condition on, roughly. The values of these about log p different Euler products, rather than p or square root p or p over log p or something values. So this is much, much less stuff that I'm conditioning on. So this will substantially get rid of this problem. So after I've conditioned on the values of all these, I'll still have quite a lot of sum of characters left over, usually average. Okay. Now the other thing is that if you look at these absolute values of these Euler products, so actually you can take the log here. So if you take the log of this, you have the log of the absolute values, you get the real part of the log of this. So basically you get the real part of the sum over primes of chi of p over p to the half plus I k over log p. These things, they behave a lot like the corresponding random objects. You can prove this rigorously by computing, so you want to control all these at the same time for different k. So you can prove this by computing sort of mixed moments of all these. And it's important here that capital P, the length of the sum, is not close to R. So you're not close to the conductor. But I said before that you can always arrange that P is a lot smaller than R, because P is x of log of L to the 1/3. So log of L might be of the order of log R, but this whole thing is always much, much smaller than R. So you can compute a lot of moments of this. Periodicity doesn't come in, and the moments here will very exactly match the moments. So the upshot of this is that, so that the character sum average that you had to start with, you can upper bound by an average of these integrals of Euler products, with the primes only going up to capital P. As an upper bound, you can do this. So this is a place where you can do it for an upper bound, but for a lower bound, this causes problems. But you can choose the range of the primes how you want for the upper bound. So you can do this with the primes going up to capital P. And then because of what I said on this slide, because the distribution of this is very close to the distribution of this thing will be roughly the same as the corresponding average in the random multiplicative problem, where the Euler product goes up to capital P, the same as here. And now you can actually use the result from the random case. So all of this was just step 1 of the random proof, but you don't need to do step 2 in the deterministic case, because at the end of step 1 in the deterministic case, you get back the same thing you had in the random case. So you can apply the bound that you had from the random case to estimate this. And you'll get something that has a saving of log log p in it, but log log p was of the same order of magnitude as log log L because of how we set things up. So you'll get the saving that you want. Okay, so let me show one final slide and then we'll finish. So as I said, it's an open problem to get a matching lower bound. In Theorem 1, I think it's probably quite hard. Some things are known. So I think the best that's known is this fairly recent result of Labratesh, Munch, and Tenenbaum by a completely different method, the combinatorial method, looking at multiplicative energy. So they prove that this is lower bounded by root x divided by a small power of log x. And for comparison here, we're expecting a bound with a log log in the denominator. So if you could get a lower bound that matched the Theorem 1 lower bound, then you could compare these moments for 2 different values of Q. And because of the way that they scale, you could deduce that a positive proportion of these character sums don't vanish. And this would tell you, roughly speaking, that for a positive proportion of characters chi mod r, the Dirichlet theta function at 1 doesn't vanish, because the Dirichlet theta function at 1 is basically a character sum of length about square root r with a kind of exponential scaling factor. And so this is certainly much less interesting than, let's say, an L function at 1/2. But what is interesting about this is that to study L functions at 1/2, if you want to get a positive proportional vanishing result, you'd usually use mollification. And here, this doesn't seem to be possible. So when you mollify at 1/2, you exploit the fact that you have a denominator square root n in your sums, and that sort of kills off some of the effect of the tails. Here, there is no denominator. So mollification doesn't seem to be an option. So it's not clear how to prove a positive proportional vanishing result in the setting, except going via this lower bound for the moment. Now, it's also not clear how to prove this lower bound for the moment. So it's not clear how to do it one way or another. But this would be an approach to doing it. If you could get a matching lower bound in Theorem 1, it would resolve it. Okay, that's what I want to say. So thank you very much.
All right, let's all unmute and clap and thank Adam for a great talk. All right, questions for Adam?
Just a quick question. How recent is this recent result that you mentioned in this last slide?
This Labutesh Munch Tenenbaum?
Yeah.
This is maybe the preprint is about 1.5 years ago, and the published version from last year, something like that.
Thank you.
Yeah, I do want to come back to modular forms because I think it's going to be quite juicy. Firstly, the Steinhaus. There isn't a unique distribution on the angles. There's something called Sato-Tate, but there are other distributions. And so the issue would be how that impacts the answer.
Okay.
If you average over all the modular forms, then these ones which aren't Sato-Tate are very rare. So they would disappear, but you might make your packet be CM forms or something. And then the issue of the multiplicativity, and that the values are not exactly 1, should be quite juicy and quite useful, in fact. And maybe you can answer a question that's in a letter of mine to, I think his name is Bachman. You'll find about, so the issue is whether there are infinitely many L functions which are positive definite on the imaginary axis. So there was some people try to prove no Ziegel zero or no real zeros by believing that these, I forget what the sums are called, Herglots or something, or Toeplitz, or you know what I'm talking about? These partial sums which remain positive, which turns out to be false. This was disproved by 2 people. Polya maybe made the conjecture, and he disproved it, and Heilbronn disproved somebody else, I can't remember. You'll see it in my letter. But there is a fantastic question of whether there's an infinite sequence of L functions for which if you restrict to the imaginary axis, it's positive definite, which would mean no real zeros for a very deep reason. And I couldn't answer the question even conjecturally because I didn't know what happens with a random multiplicative function.
Okay.
And that should predict the answer. If you make random polynomials and ask the same question, there's some beautiful work of Poonen and somebody that I referred to there, but one has to develop it for the random multiplicative function. Okay. And then you would know the truth. Okay.
So you want a random polynomial with random multiplicative coefficient.
Yeah, and it's a question about real roots of that.
So that sounds very interesting. I can mention that there is some recent work on large values of random polynomials with random multiplicative coefficients. So this is work of Brad Rogers and Jack Benatar, I think, maybe one other person. So this is kind of getting analog of classical work of Salem-Zygmund for completely independent coefficients, but in the random multiplicative space.
Yeah,
but they're not looking at zero distribution, they're looking at large values.
Right. So the question that I was asking, even for random polynomials, was very subtle and answered by Poonen. Yeah.
Okay.
Whether something happens infinitely often, that was the question.
Mm-hmm.
Not what's happening for the random guy. That's easy. But is there a sequence of L functions which have no real zeros for the reason that they're positive definite, or these partial sums are positive, which fails for most. So I'll send you the exact question.
Okay, thank you.
Do you think that open problem, which is probably hard, which is on your current screen, could be done if you average a little bit over like the primes are, like maybe not taking like a huge bunch of primes, but sort of like primes in some small neighborhood?
No. So this is sort of related to what I said when Peter asked about averaging over the conductor as well. So a kind of reasonable amount of extra averaging might increase the number of characters you have from about R to R squared or something like that. But compared with the problems that you have to overcome, so I haven't really explained what the problem is with the lower bound, but if you looked at this as a kind of example, increasing the number of things you have, increasing the size of the family from R to R squared or something like that is not getting around the issue. So the reason that the lower bound is harder than the upper bound is because for the upper bound you have holder, and that means that you can choose the range of the primes on which you condition, because you can holder away the contribution from the larger primes.
Yes.
But for the lower bound, you can't do that. So for lower bound, so you could still try to compare like a conditional second moment and a conditional fourth moment, but you'll lose something from the primes that you haven't conditioned on properly. You'll lose something from the large primes. So you can't restrict the range of the primes very much, at least if you do things in a trivial way. So this kind of business of greatly restricting the range of B that you do, that's very important for the upper bounds, won't work at all for the lower bounds.
Thank you.
More questions for Adam? All right, if there are no more questions, let's all unmute and clap and thank Adam again.